So the final section of chapter 5 is a discussion of the topic of enthalpy. And we're going to begin with defining enthalpy, and then we're going to explore the property of enthalpy to be able to perform some calculations. And the property of enthalpy that we're going to be taking advantage of is the concept of enthalpy being what we call a state function. So I'll explain that in more detail as we go through. So first of all, we need to define what we mean by the change in enthalpy that accompanies either a physical or chemical process. So the change in enthalpy, commonly indicated with delta H, that is the change in heat, or the heat that is transferred at constant pressure, often indicated QP, when a reaction occurs or when a physical process occurs. So this is going to be the heat that's transferred in an open container, or alternatively the heat that is transferred for a reaction not involving gases. And it turns out that the reason why this is so useful is that the enthalpy change, the heat that's transferred at constant pressure, is exactly the same as the energy change if there's no change in volume. So that what this really means is the enthalpy change is the change of energy of the system for any reaction that doesn't involve gases or that's in a sealed rigid container, so that the volume is constant. And that's a very, very large number of reactions. So keep in mind, and I'll just point this out now, that often people will talk about the total energy of a system and give it the symbol E, but they'll also give it the symbol U and kind of swap between those two without really talking about it. So if you see U or E, we're talking about the total energy of the system. So an important concept to recognize is that an endothermic process, one in which energy in the form of heat is entering our system, will have a positive enthalpy change, and a exothermic process, one in which energy in the form of heat is exiting our system, will have a negative enthalpy change. So enthalpy, for these reasons that I mentioned on the previous slide, is often referred to as the heat of reaction. So you'll hear people talking about things like heat of vaporization. And what do they mean by that? They mean the enthalpy change that comes along with vaporizing something. Now, what's important to recognize about enthalpy, and I mentioned this right in the opening statement, is that it is a state function. And a state function is one that only depends on the beginning and end point. That is, the change in the value only depends on where you start and where you finish, and it doesn't matter the route that you take. So for example, I always remind myself of this by putting this picture of me on the summit of Mount Rainier. So in this photo here, we'd climbed up Mount Rainier via the Emmons Glacier, right? But my height above sea level, 14,400 feet, would be exactly the same if we climbed up via Camp Muir, so via the DC route. So it doesn't really matter the pathway that we take, we always end up at the same point, which is about 14,400 feet above sea level. So the same for enthalpy in chemical reactions. When I go from my reactants to my products, the change in enthalpy of that process is the same whether I go via intermediate A or whether I go via intermediate B. So if I start at D and I end up at E, it doesn't matter if I go through A or whether I go through B, the enthalpy change will be the same because the beginning points and the end points are the same. And that's a really kind of useful concept. As I mentioned, the enthalpy change of a physical or chemical process is often referred to as the heat of reaction. Enthalpy is a function of pressure, volume, and the change in internal energy, and they're all state functions, so therefore enthalpy also is a state function. One of the important qualities about enthalpy, in addition to it being a state function, is that it is always specified for a reaction exactly as written. So when I write a thermochemical equation like this guy here, and if this is read 1 mole of A reacts with 1 mole of B to produce 1 mole of C, accompanied by a change in enthalpy of 200 kilojoules. That's for exactly how that reaction is written. So what that means, if I reverse the direction of the reaction, I have to change the sign on my enthalpy change. And so this reaction is saying 1 mole of C decomposes to form 1 mole of A plus 1 mole of B, accompanied by a change in enthalpy of minus 200 kilojoules. Now that makes sense, right? Because what this is saying is, here is A and B, and here is C, and the difference between those two is 200 kilojoules. So when I go from A to B, I have to increase the enthalpy of the system by 200 kilojoules. So it makes sense when I go from C to A plus B that I'm going to decrease the enthalpy of my system by 200 kilojoules. So when I reverse the direction of the reaction, I have to change the sign of the enthalpy change. So here's another example. This is for a physical process. So in this example, it is explained that when 1 mole of water is frozen, 6.02 kilojoules of heat is removed from the system. So that makes sense. So here we've got liquid water, 1 mole of it. And then what we're going to do is we're going to remove, should put it up there, we're going to remove a whole bunch of energy. In fact, we're going to remove 6.02 kilojoules, and we end up with solid water, right? And the difference between there is 6.02 kilojoules. Okay, that's it. So that's why this guy's got the negative sign here. This is an exothermic process. Now, if I go back the other way, I'm going to reverse the direction of my reaction. So I'm going to flip my reactants and products. And so now I'm saying that if I wanted to take 1 mole of ice and turn it into 1 mole of liquid water, I have to add heat to the system. And how much heat do I have to add? 6.02 kilojoules. So it doesn't matter the process. If I reverse the direction of the reaction, then I'm going to reverse the enthalpy change. So if I have methane being burnt, the enthalpy change for that reaction might be X. And then if I combine carbon dioxide and water to make oxygen and methane, guess what the enthalpy change will be? Minus X. So that's kind of cool. That's one of the qualities of a state function. When you run the process backwards, you get the opposite change. The other thing to recognize that is the amount of heat that is transferred at constant pressure, i.e. the enthalpy change, is going to depend on the amount of things that are reacting. So I said that this was representing this change here, 1 mole of A reacting with 1 mole of B to produce 1 mole of C, resulting in an increase in enthalpy of 200 kilojoules. So it makes sense that if I multiplied everything by a factor of 2, that the enthalpy change would double in size. So this is reading 2 moles of A reacts with 2 moles of B to give 2 moles of C, accompanied by an increase in enthalpy of 400 kilojoules, right? So that makes sense, doesn't it? You know, if you have, one slice of bread and eating that gives you 50 kilojoules of energy, then eating 2 slices of bread will give you 100 kilojoules of energy. This is like, kind of common sense. So, let's have a look at this. So here we go. We got when 1 mole of water is frozen, 6.02 kilojoules of heat is lost by the system. So when heat is lost, that means that delta H is negative, right? Delta H is going to be less than 0. Okay, so we would write something like this. 1 mole of liquid water turns into 1 mole of ice, accompanied by an enthalpy change of minus 6.02 kilojoules. So then it asks, what is the enthalpy change accompanying the melting of 3 moles of ice? Well, it's just going to be that number here times by 3, isn't it? If this is for 1 mole, and then for 3 moles, it's going to be times by 3. So first of all, we're talking about the melting of 3 moles of ice, so we have to flip our reactants and products, and when we did that, we changed the sign, okay? And then we have to, this is for 1 mole, so then we have to take into account that we have 3 moles, so we've got to multiply it by 3. And that makes sense that the enthalpy change for this process has a positive sign because we're putting heat in to take ice and turn it into liquid water. Okay, so one of the things that can catch people out with this topic is the names that accompany specific enthalpy changes, and you do need to know these names. The first one here is particularly important. So the enthalpy of formation or the heat of formation, normally indicated by delta HF, is the enthalpy change that accompanies the formation of 1 mole of a substance from its elements. So there are a couple of things to keep in mind here. These, the first is that some elements, H2, F2, Cl2, Br2, I2, P4, and S8 are not monatomic, right? So that's something, or we also have N2 and O2 in here. They're not monatomic, so that's an important thing to keep in mind. So you have to know the 7 diatomic elements, and then you also have to know P4 and S8. The other thing to keep in mind is that this is for the formation of 1 mole of a substance. So there's always just the 1 mole of a product, right? And that can mean that sometimes we have the fractional amounts of one of the reactants. So that can get like a little bit awkward. So if I was looking at the formation of, well, we've got this one here, NaCl, the enthalpy of formation is always given for the formation of 1 mole of the product. Now, sodium is a monatomic element, but chlorine is a diatomic, so we'd have half a mole of chlorine there. So you just got to be aware of that sometimes you get these reactions that are written in non-conventional forms with fractional amounts of reactants. The reason being is we're always going to be just forming 1 mole of the product. Now, the enthalpy of or heat of fusion, the name here is a little odd because we think of fusion as becoming more firm, but this is actually the enthalpy change accompanying the melting of 1 mole of a substance. So this is just going from the solid state to the liquid state, and so the delta H of fusion, you're always going to be putting energy in to make this happen, aren't we? So it's going to always be positive. Okay. The other common enthalpy change is the enthalpy or heat of vaporization. We're going to see this quite a lot throughout the course. We're going to be looking at this when we look at what we call the Clausius-Clapeyron equation later on. We will need this, and it's very similar to the heat of fusion. This is the enthalpy change accompanying the evaporation of 1 mole of a substance. So thinking about this, we're going to take a liquid and turn it into a gas. So enthalpy of vaporization will also always be a positive number. Okay, so enthalpy of vaporization will be what we call endothermic, because we have to put heat in to evaporate a liquid, and similarly to melt a solid, that also will be endothermic. The enthalpy of formation, sometimes it's exothermic, sometimes it's endothermic. It depends upon the substance. There's no consistent trend there. Okay, so let's have a look at this one here. It says when gypsum, which is calcium sulfate dihydrate, is heated to 150 degrees Celsius, so that means that we're putting heat in. It loses most of its water and forms plaster of Paris. So calcium sulfate dihydrate, we're going to put some heat in and it turns into calcium sulfate half a hydrate. There we go. Okay, so this is a heat in process, isn't it, right? So that means that the products have more heat than the reactants. So if we was going to put it this way, then we would go, this would be our calcium sulfate dihydrate, and this would be the calcium sulfate 0.5 hydrate. So the process requires an input of energy as heat, so delta H is going to be positive, and we would classify this as endothermic. All right. Now, it is important to recognize that the enthalpy change accompanying a reaction is dependent upon both the conditions of the reaction, so the pressure, volume, and temperature, and also the concentrations of the reactants and products. Often we'll talk about standard enthalpy changes that are determined under standard conditions for substances in their standard states. So just so you know, standard conditions are a pressure of 1 atmosphere, okay, and then standard states are the state of the substance at 1 atmosphere and at room temperature. And it also means the most common form of the substance. So where that really comes in is when we have multiple elemental forms of something like carbon, it's going to be the graphite form, okay, for the standard state. For oxygen, it's O2. For those other diatomic elements, it's the diatomic form, and so forth. But standard conditions means a temperature of a pressure of 1 atmosphere, and it means so a pressure of 1 atmosphere means that it's at room temperature. It means the most common form. For a solid or a liquid, it's the pure substance, and for a solution, it means that the substance has a concentration of 1 mole per liter. So it's all under kind of standard conditions. 1 atmosphere of pressure, room temperature, the most common elemental form if it's an element. If it's a solid or a liquid, it's the pure substance. If it's a solution, it has a concentration of 1 mole per liter. Now, when an enthalpy change is a standard enthalpy change, we indicate that using a degree sign after the symbol for the enthalpy change. So you can see that here. Here's the little degree sign. In fact, for any quantity where we have that degree sign following it, that means that it is a standard value where we've got standard conditions and standard states. So this is summarizing it here. Standard states of a substance depends upon its phase. For a gas, the standard state is a pressure of 1 bar. For a solid or liquid, the standard state is the pure substance. For a solution, it's a concentration of 1 mole per liter. It's always the most stable form of the element. So graphite, not diamond. And then the only other ones to keep in mind are those diatomic elements, and P4 and S8 are the most stable forms of the elements. Standard enthalpy is normally determined at a specified temperature, which is often 298 K, which is about room temperature. Okay. So we'll talk about standard enthalpies of formations, which we can indicate with delta H naught formation. What does that mean? It's the enthalpy change at constant pressure when 1 mole of a substance is formed from its elements in their standard states. So remember, like I said, it's always about formation of 1 mole of the product, and everything is in its standard state. So these labels here are indicating the phase of the substance at room temperature. The pressure is going to be 1 atmosphere, and because everything here is a gas. So we're looking to form 1 mole of ammonia from its elements. The elements are nitrogen and hydrogen, both of which are diatomic. And you can see here that I've got fractional coefficients because I'm always looking for forming 1 mole of my final compound. Now this process, it turns out, is exothermic. The system is losing heat. So what that means is, here's my N2 and H2, and then down here is my ammonia, and as I go down that pathway, heat will be given off. So I'm in the surroundings, everything will look like it's getting hotter, right? It's radiating out heat. And that's what I'm going to observe because the system is losing heat. So there's an important consequence of enthalpy changes being a state function, and that is that we can apply what's called Hess's Law of Heat summation. And Hess's Law of Heat summation states that the enthalpy change of an overall process is equal to the sum of the enthalpy changes of the individual steps. And so what that means is, if I'm going to go from here, position A, all the way over to here, position B, this is going to be an endothermic process, and then I go through C, and I go to D, and then I go to E. If I just add together all of these individual changes in enthalpy, I get the same enthalpy change as going from A to B in 1 step. Alright, so 1 plus 2 plus 3 would be exactly the same as going from A to B in 1 step. Now, that's kind of, that's pretty cool, right? The enthalpy change of an overall process is equal to the sum of the enthalpy changes of the individual steps. So here's the overall change, and these are the enthalpy changes for the individual steps here. Both of those things are equal. So we're going to kind of take advantage of this in a couple of different ways. The first way is that we're going to use this to determine, when we have a whole series of enthalpy changes, a value that is missing. So this is a series of reactions here. We're going to go from A to D ultimately, but we're going to go first from A to B, then we're going to go from B to 2C, then 2C to D. And what we want to know is, what is the overall enthalpy change? So it's similar to what I was illustrating before. We know that to go from A to B, I have to put in 150 kilojoules. Then to go from B to 2C, I have to put in another 400 kilojoules. And when I go from 2C down to D, 50 kilojoules is released. Now, according to Hess's law, the overall enthalpy change for going from A to D in a single step is just equal to the sum of all of these components, right? So there we go. Going to A to D in a single step is just these guys added together. So 150 plus 400 is 550 minus 50, 500 kilojoules overall. So that's one way of using Hess's law of heat summation. Another way of using Hess's law of heat summation is to calculate the enthalpy change for a reaction using what we call standard heats of formation. You can find a big old table of standard heats of formations in the back of your book in Appendix G. So if you just look on the table of contents for the OpenStax book and you go and click Appendix G, it'll give you big tables of standard heats of formation. So how we use these to calculate the enthalpy change for a reaction is a two-step process. We're going to consider every reaction to occur via a two-step process. In the first step, what we're going to do is we're going to take all of the compounds that are present in our reactants and we're going to decompose those guys into their individual elements. So if I've got a mole of ammonia, as one of my reactants, I would break that down into its individual elements. Now you can see that what this is just the opposite of the heat of formation of ammonia. So that step would have an enthalpy change of negative heat of formation. And if I had, X moles of that, and then I would need to multiply that by X. So for every substance that I'm doing this for, I would have a term that looked like this. It would be minus N, where N refers to the number of moles of the substance multiplied by its standard heat of formation. So for every reactant, however many reactants I've got, I'm going to calculate a term like this, and I'm going to add all of those terms together. So having performed this first step, what I've got now is all of my reactants have been decomposed into their elements. And what I'm going to do now is I'm going to put those elements back together in the form of the products. So in the second step of the reaction, what I'm going to do is I'm going to reassemble all of those elements into the products. And we know that when we assemble a compound from its elements, the enthalpy change accompanying that is just simply the enthalpy of formation. So this second step is going to be for every product, what I'm going to do is take the number of moles of that product and multiply it by its enthalpy of formation. So if I think of a reaction as being composed of these two steps, taking the reactants, breaking them down into their elements, then taking those elements and reassembling them into the products, then for any reaction, I could determine the overall enthalpy change just by adding together the enthalpy changes for those two steps. So when I do that, let's think about what the math will be. The overall enthalpy change for a chemical reaction is just going to be the enthalpy the sum for every product of the number of moles of the product times by its enthalpy of formation minus the sum for every reactant of the number of moles of that reactant multiplied by its enthalpy of formation. So just remember that the sigma symbol means the sum of all of the terms of that type that follow. So what we're going to do is for every product, we're going to take the number of moles of that product, N is number of moles, and we're going to multiply that by the standard heat of formation, which we can get from the appendix. Now, what do I mean by the number of moles of that product? Well, let's just consider our favorite reaction, the combustion of methane. I'm really talking about what the coefficient is in the balanced equation. So that's what my N is referring to. So we'll have a look at this now, how we can use these tabulated values of standard heats of formation along with a balanced equation to calculate the enthalpy change for a chemical or physical process. So here it says use standard enthalpies of formation, appendix G, to calculate the standard enthalpy of reaction for the following. So we want delta H for this guy. So for every product, we have to add together the heats of formation. So I've got one methane, and when I look in the back, I find that the standard heat of formation of methane is minus 74.8 kilojoules per mole. And then I've got two waters, so I've got a 2 there. And when I look in the back of the book, I find that the standard heat of formation of liquid water, you do have to be aware of the physical state, is minus 285.8. So when I add those two terms together, one for each of the products, this is what I get, right? So that is for the products. That term there is that guy, all right? Then I've got to subtract from that the sum of all of the heats of formations for the reactants. So I've got 4 moles of H2 gas, and the heat of formation of any element is always 0, because remember what the heat of formation is? It's the enthalpy change accompanying the formation of 1 mole of the product or 1 mole of the substance from its elements. If it's already in its elements, that's the do-nothing state. So that's why that's a 0 there. So 4 times 0 for the hydrogen there. And then we've got 1 CO2, so it's 1 times the standard heat of gaseous, standard heat of formation of gaseous CO2, which is minus 393.5. So this term that's in parentheses here for my reactants is that guy. So I subtract standard heats of formation of my products from the standard heat of formation of my reactants, and I get the overall enthalpy change for that reaction. There you go. It's fairly straightforward. So that's another way that we use Hess's law of heat summation. Now there's a third way where we're going to use Hess's law of heat summation, which is where we're going to have a bunch of reactions and we're going to mix and match those reactions and add them together to get the enthalpy change for a new reaction. So I'll show you what I mean. So if we look at the formation of sodium chloride, we can consider it as occurring via the following 5 steps. Now this would be a really silly way of making sodium chloride. So we're going to begin with elemental sodium and half a mole of chlorine gas. And at room temperature, sodium would be a solid and chlorine would be a gas. Then I'm going to heat it up and I'm going to put in enough energy to turn my solid sodium not into a liquid but into a gas. I'm not going to do anything to my chlorine, so that would require a certain input of heat. Now what I'm going to do is I'm going to break apart my chlorine molecules, and I've got half a mole of those guys. I'm going to break that bond. I'm going to break these apart into individual chlorine atoms. And bond breaking always requires an input of energy. So that will be my second step. And then what I'm going to do is I'm going to take my sodium atom, and sodium, if you remember, has 11 electrons, and I'm going to pull an electron off it. So it only has 10 electrons. I'm going to rip an electron off this. And obviously breaking an electron away is going to require an input of energy. So now I've got a sodium ion and a chlorine atom. What I'm going to do next is I'm going to take my chlorine atom. It has 17 electrons. I'm going to add an electron to it and form a chloride ion. So I'm just kind of moved all of these over here just to make it simple. So in this process, I'm adding an electron to this. And when I do that, energy is released. And here I have a chloride ion. So there's my 4th step there. And finally, what I'm going to do is I'm going to allow my sodium ions and my chloride ions to combine. They're going to electrostatically attract one another and form solid sodium chloride, and that will be my 5th step. And what I know, because I've got appendix G, where I've got my standard heats of formation, is if I do this in one step, if I form 1 mole of sodium chloride from the elements, from its elements in their standard states, under standard conditions, then according to the appendix, minus 411.2 kilojoules of heat would be released. Okay? Alright, so what I also can determine is that the enthalpy change for the sublimation of sodium is 109 kilojoules. The enthalpy change for what we call the dissociation of half a mole of chlorine molecules, the energy I have to put in to make that happen is 120 kilojoules. The enthalpy change for ionizing 1 mole of sodium atoms is 495 kilojoules. The enthalpy change for ionizing 1 mole of chlorine atoms is minus 339 joules, but the enthalpy change that accompanies the combination of a sodium ion with a chloride ion to form 1 mole of solid sodium chloride is unknown. But I do know if you add all of these things together, that the enthalpy change for all of those steps combined, we can cancel out terms here to see what the overall reaction is for doing that. There it is. That would give that reaction. The enthalpy change for this overall reaction, the sum of those 5 steps, is minus 411.2. So you can see if we just let that guy be x, it would be pretty easy to solve for what x is. So that's what we're going to do, isn't it? Minus 411.2 is equal to 109 plus 120 plus 495 plus minus 349 plus x. And now x has to be a negative number. We've got to be going down here, haven't we, right? We know that. So let's see what we get when we do that. So here I am. This is x is my 5th enthalpy change here. And as I said, it's going to be minus 411 minus all of these other things here that will give it to me. And when I do that, I get a large negative number as expected. Okay, so that's it. So it doesn't really matter what way I slice it or dice it. If I go in one step, the enthalpy change is minus 411.2. And if I go around this 5-step process, the enthalpy change will still be minus 411.2. All right. So this is a couple of repeat slides. Remember that I said that the enthalpy change of a process is specified for a reaction exactly as it's written. And there were a couple of things that we pointed out. One was if we multiplied our reaction by some kind of factor, in this case it was 2, then we have to multiply our enthalpy change by the same factor. The other thing that we pointed out was that if you reverse the direction of a reaction, and here we have, in this case, we've got the freezing of water and the melting of ice, we have to reverse the sign of the enthalpy change. So obviously, in order to freeze water, we have to take heat out, but if we want to melt ice, we have to put an equivalent amount of heat back in. So if you keep those 2 points in mind, you'll see another way that we can use Hess's law. So the other way that we can use Hess's law is we can take a series of reactions where we know the enthalpy changes, and then we can reverse and multiply and add those reactions together to come up with a new reaction that we're able to determine the enthalpy change for without actually even performing the reaction. And that can be really, really useful. So in this case, I've got these 3 reactions here involving oxygen, ozone, and nitrogen oxide and nitrogen dioxide. And I'm going to combine this thermochemical data together to calculate the delta H for a new reaction. And I'll show you how I do that. We're going to exploit Hess's law of heat summation, which means we can add together enthalpies for individual steps, along with those 2 rules that we had before for reversing and multiplying reactions. So what I got to do is I've got to find something that has NO on the reactant side. And I only have one reaction that has that. So I'm going to take one lot of that guy and write that down along with its enthalpy change. Now, what you'll notice though is that I've introduced ozone to the reactant side, and in my desired reaction, I don't have any O3. So I need to get rid of that O3. So I'm going to need 1 mole of O3 on the product side of my of a reaction. And when I look up here, I've got 2 reactions that involve O3, but I don't want to use another one of number 3 here because that's just going to add in more NO and throw that out. I want to take this guy, but I need my O3 on my product side, so I'm going to have to reverse it by, and I'm going to multiply the enthalpy change by -1 when I reverse this reaction. Because there's 2 of them there, I'm also going to halve this reaction. So I'm going to multiply the enthalpy change by 1/2. So when I do that, what I'm left with is this 3 on 2 O2 gives me a 103, and the enthalpy change for that will be, it now becomes plus 427 on 2. So I've multiplied the enthalpy change of my original reaction by -1/2. Okay, I'm getting closer. So now I get rid of my ozone there. That's good. And then I've got 1.5 O2s there. So I get rid of all of those O2s, and that's going to leave me with half an O2. Okay. Yeah. NO plus half an O2 gives me NO2. I'm not quite there yet. I have to introduce an O onto the reactant side, and I need to get rid of this half O2, make that disappear. So how can I do that? Well, I've only got one reaction that has an O in it, but it's similar to before because the O in my given reaction is on the product side and I need it on the reactant side, so I'm going to have to multiply it by -1. And then I've got 2 O's in this guy instead of just the 1, so I also have to multiply it by 1/2. So the enthalpy change for that reaction will be -495 on 2. And now half an O2 cancels, half an O2 cancels, and yep, I'm left with what I want. NO plus O gives me NO2. The enthalpy change for this whole process is just going to be these 3 numbers multiplied together, but added together, sorry, 199 plus 427 on 2 plus -495 on 2, and the units there would be kilojoules. So just using those very simple rules where if we reverse the direction of a reaction, we multiply the enthalpy change by -1, and if we multiply a reaction by some factor, we multiply the enthalpy change by the same factor, which in this case was 1/2. And then using Hess's Law of Heat summation, it says if we add a series of reactions together, then the enthalpy change will just be the sum of the enthalpy changes for that series of reactions. So they're kind of complicated. They're a little bit like a little crossword puzzle, a little Sudoku puzzle. You just got to kind of get the pieces to fit together to give you the desired overall reaction. But they're not impossible, and there are some worksheets that are going to help you practice do this. Okay, so that concludes our video on enthalpy of chemical reactions. This is the final video for chapter 5 and also the final video for chemistry 161. So congratulations, you made it.